Hello friends, I am Dr. Kulkarni and today I'll be talking to you about the sample size determination in epidemiological studies. The necessity of determining the sample size is for two reasons. One is that the results become invalid if the study is done on smaller size than it is actually required. And the second is that you may unnecessarily be doing study on relatively larger sample size, even though the smaller sample size would do. So on one side, the smaller size, the sample size that you will be doing study on may be less or it may be more. In either counts, it will not be advisable. The prerequisites for the sample size calculation are that the statisticians require some information because the sample size involves some statistical calculations, and the statisticians require some information, and this information is required to be given by the investigator. Some of this information can be given from the literature or pilot because it is based on the previous studies or the pilot study done by the investigator. Some information requires the knowledge of basic statistics, and every individual who is undertaking an epidemiological investigation is required to have some basic knowledge of basic statistics. In analytical and experimental studies, the sample size is different for hypothesis testing and testing for the difference. So in analytical or experimental studies, the hypothesis could be of association type or it could be of difference type. Whenever the hypothesis is of difference type, the investigator may want to either say whether the null hypothesis is accepted or not accepted. So that is the hypothesis testing in the epidemiological studies. Or they want to find out the actual difference in the variables because the question is of difference type. And the sample size required for these two will be different, and hence the investigator has to tell the statistician whether the study sample is required for testing the hypothesis or whether it is for testing and estimating the difference between the variables in the research question. This is one concept which every person who intends to do an epidemiological study must know, and that is the alpha error. Alpha error is the significance level of the test, and it is the probability of rejecting a true null hypothesis. It is also called type 1 error. The commonly accepted level of alpha error is 0.01, 0.05, or 0.1. In terms of percentages, it could be mentioned as 1%, 5%, or 10%. In clinical trial, a large alpha error would lead to bringing a relatively useless drug in the market. You don't want to bring a useless drug in the market. And if you keep the alpha error larger than 0.1, then there is a possibility that you may be bringing a drug which is not effective, and you may conclude that the drug is effective. So such type of conclusion, if it is to be avoided, then the alpha error has to be carefully set up. The confidence level is another statistical concept. It is the probability of correctly accepting a true null hypothesis, and it is denoted by 1 minus alpha, or 100 into 1 minus alpha. So if the alpha is decided, naturally the confidence level will also be automatically decided. For example, if the alpha error is 1%, the confidence level will be 99%. If alpha error is 5%, then the confidence level would be 95%. If the alpha error is 10%, the confidence level will be automatically decided at 99%. So if alpha error is mentioned in terms of percentage, the confidence level will also have to be mentioned in terms of percentage. But if alpha error is mentioned here as 0.01, then the confidence level will be 0.99. If alpha error is mentioned here as 0.05, then the confidence level mentioned will be 0.95. The higher the confidence level, higher is the required sample size. So the investigator has to strike a balance between the feasible sample size and the technically required sample size. Some balance will have to be achieved. Then another concept is the beta error. Beta error is the probability of failing to reject a false hypothesis. It is also called as type 2 error. Commonly accepted levels of beta are 0.1 or 0.2%, 0.2. In terms of percentage, it is 10% or 20%. In clinical trial, a large beta error would lead to preventing a good drug from entering in the market. So we don't want to bring a useless drug in the market. Similarly, we don't want to prevent a really good drug from entering the market. So there has to be a balance between the alpha error and beta error so that you commit the minimum alpha error and minimum of beta error. Power of test is the other side of the coin for the beta error. The power of the test is the probability of correctly rejecting a false null hypothesis. It is denoted by 1 minus beta, and in terms of percentages, it would be 100 into 1 minus beta. When beta is selected, the power of test is also automatically selected. So if the beta is 10%, the power is automatically 90%. The beta is 20%, the power of test is automatically 80%. If we say that it is beta error is 0.1, then the power is 0.9. If the beta error is 0.2, the power is 0.8 automatically. The higher is the power of the test, higher will be the sample size. Other things remaining equal, higher the power of the test, higher is the sample size required. Then when the alpha and the beta errors are decided, one has to know the corresponding Z values. These are also called as Z1 minus alpha by 2, Z1 minus alpha or the alpha error, and Z1 minus beta. This represents the number of standard errors from the mean of the population. So Z1 minus alpha and Z1 minus alpha by 2 and Z1 minus alpha are the functions of the confidence level, while Z1 minus beta is the function of the power of the test. In this presentation, we will be using Z1 and Z2 will be used instead of Z alpha or Z beta respectively. So if the alpha error is 0.01, the confidence level is therefore 99%. And whether the test you are using is one-sided or two-sided, depending on Z alpha, will be 2.33 or 2.58. So for one-sided test and alpha error of 0.01, the Z alpha or Z1, which will be utilized in this presentation, will be 2.33, and for two-sided test, it will be 2.58. This is the commonly accepted level of alpha error, that is 0.05, and the confidence is 95%. So for one-sided test, Z alpha is 1.65, and for two-sided test, it is 1.95. For alpha error of 90%, the one-sided test, for one-sided test, Z1 will be 1.28, and for two-sided test, it will be 1.65. Similarly, the beta error is 10%, the power of the test is 90%, and the Z beta or the Z2 in this presentation will be taken as 1.28. If the beta error is 0.2, the power of the test is 80%, then the Z beta or Z2 in this presentation will be taken as 0.84. In some of the problems of determining the sample size, we will have to mention the precision. With what precision you want your estimate to be. So the difference between the guesstimate, that is the guessed estimate of a variable, and the minimum and the maximum values you accept or acceptable to you is the precision. So when it is expressed in absolute value, it is called as absolute precision. But when it is expressed in terms of percentage of the guesstimate, then it is called as relative estimate. For example, if this is the guesstimate, that here on the scale, the guessed estimate of the mean is there. So you will have to mention as to what will be the minimum acceptable value and the maximum acceptable value of that mean, or the uh, universe value, or the population value that will be acceptable to us. This type of information is required mostly for the cross-sectional type of epidemiological studies. Relative precision, when the absolute precision is expressed not in terms of absolute terms, but as a percentage of the guesstimate, it is called as relative precision. Other things being equal, lesser the value of the precision, more is the sample size required. So now these are the common situations wherein the sample size determination will be required. For example, if it is a cross-sectional study and we are trying to estimate the population P, that is the prevalence of the disease. So here P is a nominal variable. So what we require is what is your guess about the prevalence of the variable in the population. This you can obtain from the previous studies, or you can conduct a pilot study, and that information can be used in the formula that we will be giving and discussing later on. The D is the relative, D is the absolute precision, and Z1 is the alpha error that is acceptable to us. Z1 is the Z value associated with the alpha error that you have chosen to. So if these three, if the information about these three, that is your guess about the population prevalence or the population proportion, and the D, that is the uh, absolute precision with which the P is to be calculated, or P is acceptable to you, and the Z1, that is the function of alpha associated with the test that you have selected. So this information will be required. If it is an estimation of the population mean, so M is on the ratio scale, because it is dealing with the mean. The M is on the ratio scale, or it is on the interval scale. So what we require is, what is your guess about the population mean that you are trying to estimate? You will have to tell as it may be such and such value, which can be obtained from the previous literature or by doing a pilot study, and the standard deviation of this mean. This is the standard deviation of the mean, the precision with which you want to estimate of the mean, and Z1, that is the Z value associated with the alpha error that you have selected. In a case control study, you could have two objectives. One is the testing the hypothesis, or odds ratio is equal to 1. The null hypothesis is odds ratio is equal to 1. And the alternate hypothesis could be either a one-way hypothesis or a two-way hypothesis. Or your aim could be estimating the odds ratio, or you could be aiming both of these. So your aim is to test the hypothesis, a null hypothesis, OR is equal to 1, and also estimating the odds ratio within a given confidence interval. So what information we require is the exposure in the probability of exposure in the study group and the probability of exposure in the control group. And these are on the nominal scale. That's why we are selecting the case control study. So here we will have to give the information about the P1 and P2. What is your estimate about the probability of exposure in the study group? What is the probability of exposure in the control population? Then if this information is given, then we can have an idea about the probable odds ratio that we are expecting. Out of these three, P1, P2, and odds ratio, any two can be given, and the other third one can be calculated. And Z1 and Z2 are the Z values associated with chosen level of the alpha and the beta error. The study is of the clinical trial type, that is of the superiority design. Then your objective could be testing the hypothesis and estimating the difference of P1 and P2, where P1 and P2 are the nominal, are the variables measured on the nominal scale. So P1 and P2 are measured on nominal scale. So the information that is required by the statistician is P1, that is the, say if it is a cure rate, then what is the cure rate of the study intervention what is the cure rate with the control intervention, and Z1 and Z2 are the Z values associated with the chosen level of the alpha and beta error. So here, this information will be required when the variable P1 and P2 are measured on the nominal scale. If it is a clinical trial and the variables are measured not on the nominal scale, but on the ratio scale. So we are testing the null hypothesis, say between M1 and M2. M1 and M2 are the two means hypothesized. So our objective could be testing the null hypothesis of M1 is equal to M2. Or our objective could be finding the difference, estimating the difference of M1 and M2. So M1 and M2 here are either on the ratio scale or they are on the interval scale. So the information required for calculating the sample size is M1, that is the expected mean, M1 in say study group, M2 in the control group, the standard deviation of M1, the standard deviation of M2, expected standard deviation, and Z1 and Z2 are the are the Z values associated with the chosen values or chosen alpha and beta error. The sample size could be calculated with the use of sample size calculating softwares. And these are some of the popular softwares, Epinfo and OpenEP. These are these softwares freely available. And you can download these on your computer from the website. You can search for Epinfo or you can search for OpenEP on the Google. And that will take you to the requisite website from where you can download and then install the respective software. The power and sample size calculator is another very popular type of software for calculating the sample size. So the Epinfo, OpenEP, and power and sample size calculators have the facility for calculating the sample size for about 5 or 6 types of study designs. There could be standalone calculators. They are available on the internet. You can search for these and you get these standalone calculators. The standalone calculators will help you in calculating the sample size for a particular type of study design. For example, you can get the calculator for case control study, either unmatched case control study or matched case control study. You may get the standalone calculator for calculating the sample size for the clinical trial, say superiority design, where the variable in question is, say, on ratio scale or on the nominal scale. But the problem with these softwares is, number one, is they have got limited or few study designs. They give you the help you for limited study designs. And if your study design is not included, then you have a problem of how you calculate the sample size. Second, they do not give the formula for calculating the sample size. These softwares usually do not give the formula with which the sample size is calculated. And when you are going to present your report or you are sending the article for publication, the referees may ask for the formula used for calculating the sample size. And if you are doing calculating the sample size with these softwares, the formula may not be available. So you will have to then search for the formula and you may not know which formula the software has used. So that is the problem. So in order to solve some of these problems, and in order to make the software user-friendly, and in order to see that the sample size calculation is available for a larger variety of epidemiological studies, I have prepared MS Excel-based application, which will help you in calculating the sample size. So here, the sample size calculation for more than 20 common study designs is available. With it, there is one sheet for each study design. So about 20 to 25 study designs are covered, and for each study design, there is a separate MS Excel sheet used. On that sheet itself, you will get the formula used for calculating the sample size with this MS Excel application. And the reference for formula is also given. So when you publish the article using this MS Excel based application, you have got the wider choice of the study designs, so that you do not have to search for your own study design on the internet and get frustrated. Once you find out the exact Excel sheet in the bunch of the file of the Excel sheet application, then the formula for used is also given, and the reference for formula is also given. All of these you can freely use. And another advantage of this MS-based application is that it is freely available. I don't charge anything for using this software. But nevertheless, let us first of all see how the sample size will be calculated with the help of the formula. So this is the first example, the estimate of population P in a cross-sectional study. So these are the prevalence studies. Here the P is the population proportion, that is the prevalence of a particular outcome or the disease. So that is your question, and you want to undertake the sample survey for that, and you want to find out what will be the sample size required. So here n, that is the sample size, is equal to Z1 square and into bracket P into 1 minus P divided by D square. And n is the sample size, Z is the level of alpha, Z is the Z value associated with the alpha error that you have chosen. P is the estimate of the proportion that you expect in that population, and therefore 1 minus P will be deducted, P will be deducted from P. And D is the precision with which you want to have your estimate, with what precision you want. So nearer your expected value is nearer to the P, that means you want to with a greater precision. And the D value will be less and less. And if the D value is less, then the sample size will be more and more. This is an example of this type of exercise. In an epidemic, the investigator wants to know the proportion of persons affected with 2% absolute precision and 95% confidence. So there is an epidemic of a disease, say typhoid epidemic has occurred, and the investigator wants to undertake a rapid survey in that village or in that town, so that he gets an idea as to how many cases are prevalent at that point of time. And he wants the estimate to be with the 2% absolute precision and 95% confidence. He has a guess based on the cases admitted in the hospital that about 4% of the population might have been affected. So that is the idea. So here P, that is the guess of the population P, is 4%. The confidence is 95%. So the Z value is 1.96, and the D, it is 2%. So D here is the 2, because this is in percentage, so this is also in percentage. If this is mentioned as 0.04 instead of 4%, then this would be 0.02. So this is put in this equation. So Z is 1.96, so 1.96 square into 4 into 100 minus 4 into 2 square. So 3.68, 0.79. So you can round it up to say 370. So if you undertake a sample survey, the sample being drawn with a scientific method from that town or the village, you will get estimate within 95% confidence limits. So that is how the sample size is calculated if your problem is something like this, that is estimating the population P in a cross-sectional study. Estimating the population M. So here the variable is not the proportion, but the variable is the population mean. And we want to do it in a cross-sectional study. So M is the mean, which is a quantitative variable measured on ratio scale, and D is the absolute precision, and S is the standard deviation of M. So the guesstimate of M and its SD is required, as well as the D will have to be mentioned. And with what confidence you want to measure, and that will give you the corresponding Z value. So we want to estimate the mean hemoglobin percentage of female employees of an organization based on the sample. The organization is there, and you don't want to study all the individuals, but you just want to do a sample survey on that. So our guess is that the mean hemoglobin is 10 grams percent. The estimate of the standard deviation based on the previous study or based on the private study is 3. So 3 grams percent is the standard deviation. The confidence level is 95%. So and two-sided test is there. So the Z value is 1.96 and the precision is 0.5. So we want, if the mean hemoglobin is between 10 plus minus 0.5, that is 9.5 to 10.5, it will be okay for us. So that is what is the mean of the precision expected over here. So this is how we calculate the sample size. The n is equal to Z1 square plus standard deviation square plus the precision square. So 1.96 into 3. 3 is the standard deviation over here, and 0.5 is the precision that we are expecting. So the value is 1.3829. So you can round it off to 140. So 140 individuals randomly drawn and their hemoglobin will be measured. That will give you a fair idea of the hemoglobin of the employees of that organization, female employees of that organization. Note that here the mean of the variable is not required for calculating the sample size here. Nowhere the mean is mentioned over here, but you require standard deviation. And for that standard deviation, you require the mean. So although for calculating the sample size, the mean is not required, but for knowing the standard deviation over here, we require the standard deviation. This is an example of a case control study. And here the null hypothesis that OR is equal to 1. That means the proposed X factor is not a risk factor for the disease. That is what is the null hypothesis. And it's a case control study, and the outcome is on nominal variable. Outcome, that is the person suffers from the disease or does not suffer from the disease. That is what the outcome is like. So here R is the ratio of the controls to the cases. In this formula, R is the ratio of the cases to controls. So how many controls you want per case? If you want only one case per one control per case, then R will be equal to 1. If you want two controls per case, then R will be equal to 2. So R plus 1 divided by R is utilized in this formula. For this, it is required. Z is the Z value associated with the set level of the alpha. So whether it is one-sided test or two-sided test, that will decide the Z value and the confidence level associated with. And Z2 is the power of the test that you are expecting over here. And P1 is the proportion of the individuals exposed probably in the study group, and P2 is the proportion of individuals exposed in the, if this is study group, then this is control group. P1 could be study or P1 could be control. It doesn't make any difference because ultimately we are squaring over here. The difference is going to be squared. So even if it is negative difference, it will be squared. And P is the average of P1 and P2. Here P is the average of P1 and P2. So that value, when once you know these values P1 and P2, it is the average, arithmetic average of P1 and P2. Here the Z is the Z value set for the given Z1 is the Z value set for the alpha error, and Z2 is the value set for the beta error. So here is the actual example for the case control study. In a pilot study, it was found that 8% diabetics had the family history, while 2% non-diabetics had the family history. A large study is planned to find out whether the family history is a risk factor for development of diabetes. That is what we want to find out in this study. So family history there could be family history, or there couldn't be. There is not family history. So it is a nominal variable measured. It is a variable measured on the nominal scale. So in a pilot study, it was found that the 8%. This is a hypothetical example, and in the hypothetical study, it was found that 8% diabetics had the family history, while 2% non-diabetics had a family history. And we want to do a large study to test this hypothesis. So here we were R is equal to 1. That means we want one case, one control per case. Alpha is 0.05. So the Z1 is 1.96. And this is a two-sided test that we are going to take. That's why it is 1.96. And beta is 0.2. So the Z2 is 0.84. P1 is 8%. So here P1 is taken as 0.08. P2 is 2%. So here we take it as 0.02. And the average of this 0.08 and 0.02 is 0.05. That is the P value. It is given by adding these and dividing it by 2. And this is the formula. used that was given you previously, and putting these values in the equation, the values which are given over there, here is 1. So it will be ultimately multiplied by 2 plus 1 divided by r. And the respective z values and the p value and p1 and p2 and it squared, these values are put. So the value that is given, n, is 207. So we will require 207 cases, that is diabetics, and 207 controls, that is the persons, non-diabetic persons. And these will have to be compared. And the cases, that is the diabetics, and the controls, that is non-diabetics, will have to be chosen by the rules governed by the unmatched case control study. In example 3, if that sample size which was calculated for testing the null hypothesis. But here, if you want to find out the odds ratio, estimate of the odds ratio with a 95% confidence, then this particular formula is to be used. So here, what we require additionally is this E, eta. This is the Latin word eta square. Otherwise, all the things have already been explained. So Z1 square and all these things are there. So E is the relative precision, 0.5 for this. If the relative precision is 0.5, then we put it 0.5 and we find out the log to the base of E of this value and square it. And we put the respective values in this formula. So putting the values, it is 570. So if this study has got both the objectives is of testing the null hypothesis, and the objective is to find an estimate of the odds ratio, then we calculate the sample size for both. That is for testing the null hypothesis, which is 207, and 517 is the sample size if your objective is to get an estimate of the odds ratio. So higher among these is 517. So we take 517 as the minimum sample size for that particular study, provided the values given P1, P1 and P2 and eta are there as per used in this formula. So if it is a clinical trial and you want to test the hypothesis P1 is equal to P2, therefore the study design is comparing the cure rate, for example, or the mortality rate of the two drugs. So P1 is, say, the cure rate or mortality rate with the test drug, and P2 is the mortality rate or the cure rate with the standard or the control line of treatment. So here the values required is Z1, which is the Z value associated with the alpha error that you have chosen or the confidence you have chosen. P1 is the outcome, probability of outcome in the study group, and P2 is the probability of outcome in the control group, and P is the arithmetic average of P1 and P2. And you put the values in this equation. So P1 and P2 are the outcome variables measured on nominal scale, and P is the arithmetic average of P1 and P2. Z1 is the Z value corresponding to the confidence level selected. Z2 is the Z value corresponding to the power of the test that we are using. So Z1 is used over here and Z2 is used over here in the formula. So this is an example. Complication rate of a new method is 5%, and for a controlled surgical method, it is 15%. So this is not a clinical trial, but this is an experimental study because no drug is there. We are comparing the two intervention methods, which are the surgery done for a given condition, with the criteria for inclusion and exclusion of the patients are decided and have been mentioned in the material and methods. So the complication rate is 5% for the new method, and for the established control method, it is 15%. So the pilot study was conducted and it was found that it is 5%, that is less in the new study design. So what would be required minimum sample size to test the null hypothesis P1 is equal to P2 against an alternate hypothesis of P1 is less than P2. So here the hypothesis is one-sided. Here the hypothesis is not two-sided, it is one-sided, and it is 95% confident. So 1.65 is the Z value. If it would have been two-sided, then this would have been 1.96. And Z2, because the power of the test is 80%, the Z2, that is the Z value associated with the corresponding beta value, it is 0.8. So the information required is this, that is the proportion of the outcome in the test and the control intervention is 5%, that is 0.05, 15% here, therefore 0.15. P1 and P2 divided by 2, that is the P is 10%, so it is taken as 0.1 over here. Confidence level in Z1 is 95% one-sided, so alpha is 0.05, so the Z1 is 1.65. And the power of the test is 80%. So the Z2 is 0.84 in this case. For the testing the null hypothesis, the P1 is equal to P2 using the formula given below. This will be the formula used. This is the Z1, and this is the Z2, and the values given in the previous table are put, and the value calculated is 30. So for study group, we will require minimum 30 individuals, and for control group, we will require 30 individuals. So total 60 operative procedures will have to be performed, 30 by the experimental type of, that is the new type of operation, and 30 by the established type of technique, and you can then test the null hypothesis P1 is equal to P2. On the contrary, if you want to estimate the difference of P1 and P2, what is the P1 and with the 95% confidence limit, and if you want to measure this with an absolute precision of 2%, the values Z1 and all those things are already explained, and D is the precision, absolute precision over here. So, and if you put these values in this equation, the 642 is the sample size. So you can find here that for testing the null hypothesis, the sample size required is 30 only, while for estimating the difference, the sample size is 642. So if you have both the objectives, then naturally you should take 642 as your sample size. So that finishes the presentation over here. I would like to give a demonstration of the Excel software, Excel-based application over here, which has been prepared by me. And this part of the presentation deals with the demonstration of the Excel sheet, the Excel-based program, Excel-based application that I have prepared for calculating the sample size. The peculiarity of this program is that it will give you, or it will help you in calculating the sample size for about 20 to 25 different types of study designs. And you need not install this program, but you just have to obtain this file from me and get it copied on your file. I'll give you the email ID wherein you have to contact me for getting the this application, which you copy on your computer and then start using it directly. The requirement is your computer should have the Microsoft Office installed in your computer, and it should have the MS Excel version on your computer, and then you can very well start using it directly after you copy these files. It is in the form of MS Excel file which has got so many sheets. So it's a collection of sheets in one file only. And the first sheet is labeled as index, and the rest of the sheets are labeled as P1, P2, P3, and M1, M2, M3, something like this. And you'll have to go to the index sheet first of all. Then here you will find all the sheets numbered over here according to what is the variable in your study, whether there is one or two or more than two samples. Like in this case, it can work for 3 to 5 samples. 3 to 5 samples if it is a proportion, and if it's an observational study. Then you have to check the study type, whether it's a clinical trial or whether it is unmatched case control study or the matched case control study, and whether it is testing the superiority or non-inferiority hypothesis or equality of two proportions and like this. And this gives you the sheet number. So, for example, if your study involves a proportion and there is only one sample and it's a cross-sectional study, so it is mostly estimating the population prevalence. So in that case, you will have to use the sheet number P1. So you find the sheet number P1 over here. So here is the sheet number P1. The sheets have been named in such a way that, for example, if it is a proportion, the variable is proportion, then the name starts from P and P1, P2, P3, something like this. And if the variable is mean, then the sheet label starts from M, M1, M2, M3, something like this. And the miscellaneous sheets are given different numbers. So we want to, so for example, this is we want to calculate the sample size for this type of example. So you go to the sheet number P1. And here you will find the certain instructions are given. And you will have to enter the values only in the yellow cells. You cannot enter the values in the red cell. For example, enter the values in the red cell, such error message crops up. You will not be able to make any entry over here. So you are only permitted to make the entries in the yellow cells. The remaining things which are seen in the form of figures are calculated automatically. So now in this case, you are doing a cross-sectional study and you have to write the population size. If you do not know the population size, 0 if unknown. So I'm doing a study in a, say, primary health center, the population of which is say 30,000. And I want, and the epidemic has occurred. And I want to know what is the sample size required if say 4% of the population has been affected. So it is the 4% is 0.04. So that we have entered over here. Then what is the confidence level? So you have got options over here which will crop up in the form of a drop-down menu, and whether it is 90%, 95%, or 99%. Usually we do it for 90%. So that value is automatically entered. Then you mention the absolute precision. So this value has to be less than P. So this value, the value which you are going to enter over here has to be less than this. In fact, it has to be some fraction of it. So you cannot enter the value like 0.04 over here, or 0.05 will be accepted, but it will not be proper. So we enter 0.02 over here. So precision is 0.02. So the sample size required over here, the minimum sample size with the known population size is 365. The sample adjusted for the design effect is 1. So if the design effect is to be entered only if you're not resorting to sampling size, which is simple random sampling. If your sampling is something other than simple random sampling, then only the design effect is to be entered. If your sampling method is simple random sampling, the design effect is supposed to be 1 only. So 365 individuals, 365 is the sample size required if the in that primary health center which has got a population of 30,000 and the prevalence of the entity you are surveying is say 4% with 95% confidence and with 2% absolute precision. So that's how you calculate. You can play with over here with different percentages and different prevalences and different the confidence intervals. So like this you can do with for the when you are dealing with estimation of population proportion. Now suppose there is another example over here, and you are dealing with you have to go to the index, and suppose you are dealing with the clinical trial. There are two samples, and it is a proportion. So it is like dealing with the cure rate or mortality rate. So the clinical trial superiority or in the superiority hypothesis is there. So you go to sheet number P7. So you go to sheet number P7 over here, and it is asking you for this information in the yellow cells. you will have to mention. So here now, anticipated response rate with the standard treatment. So standard treatment, what is the anticipated cure rate? 70% for 70%. Suppose for the established line of treatment, the cure rate is 80%. So we write 0.8 over here. Then what is the anticipated response rate with the new treatment? We expect it to be more than this. Suppose it is 95%. The anticipated cure rate is 95% with the new drug. Then the type 1 error. So the type 1 error, you get a drop-down menu, and usually the level set is 0.05. Then set the level of type 2 error. So type 2 error is, we have got option over here again, and the usual level is 0.2. This is been, we are guided over here that the usual value is 0.2. And superiority and the non-inferiority margin, you'll have to mention over here. What is the superiority or the non-inferiority margin that you mention over here? And the superiority or the inferiority, non-inferiority margin is 0.2. Then in that case, the sample size for group A by method 1 is 14, and sample size for group B by method 1 is 7. So what is method 1 and what is method 2 is explained over here. Now here is the important thing is that the source and the formulas are given. Source and the formulas are given, and the source is this is the internet source over here, and the formula is given over here. The formula by which the PA and PB are fed over here is given over here, and accordingly the sample size is calculated. Sample size is calculated for NA. Here the sampling ratio is given. Sampling ratio is NA upon NB. NA is the control group, and that's why they double over here. Double figure is here. If you enter over here as 1, then both the groups, because the ratio is 1, that is you want equal number in the study and the control group. So the equal numbers is given, and the sample size therefore is 11 over here. So if the anticipated response rate with the standard treatment is 80%, with that of the new treatment is 95%, 0.95, that is 95%. If the level of the alpha error is 0.05, level of the beta error is 0.2, and the superiority non-inferiority margin is 0.2, and you want a sampling ratio of 1, then the sample size required will be 11 in each group. Then suppose we want any for the means. We go till now we discussed the example of the proportions only. We do a cross-sectional study and we want to estimate the population mean. For population mean, we want to estimate. Suppose we want to estimate the level of the hemoglobin level of in an institution. So this would be the appropriate sheet that will be, and this M1 is the sheet. So we go for sheet number M1 over here. And it is now asking you, what is the population size? So you are doing it in an organization, say like a big factory or a big educational institute. Suppose the number of the persons in the educational institute is 1,000, or say it is 2,000. 2,000 individuals are working in that college. And your guess about the population mean is say 11 grams per cent. And the standard deviation of that mean is say 2 grams per cent. And you want to estimate it with 95% confidence, and the absolute precision, which is around over here, is say 2 grams per cent. So the sample size required will be only 8. Only 8 individuals will be there. This is because the absolute precision over here is quite large. You can, if you use the absolute precision as 1, then the sample size would be 32. So 32 individuals drawn randomly from the population of 2,000 will give the idea about the hemoglobin level, provided this estimate, provided the standard deviation are correct. If the standard deviation is more, then naturally the sample size required is also more. So more the variation in the population, more will be the sample size required. So this is how, and you are supposed to enter the values only in the yellow cells, and the rest of the values will be calculated automatically. This is the formula used, which is given over here. and the reference from where this formula has been derived is given over here. You can use you can give this formula in your report. You can quote this reference in the report of your study. Then another example is, say, suppose you are going to do a clinical trial of superiority or inferiority hypothesis, and M6 is uh, therefore the sheet that you will have to find out. So we go to the sheet number M6 and it is open for us. And you enter these values over here. The mean of the group A is 10. The mean of the group 2 is, say, 13. Then the standard deviation of the group 1, standard deviation of group 2 is given over here. Alpha error, beta error is entered over here. And K is the uh, sampling proportion. That is how what is the ratio of the number of individuals in group A and in group B. So suppose it is 2, and the superiority or non-inferiority margin is, say, 2 over here. So then the sample size required is 12 in the B group and 24 in the A group. And this is the formula used over here, and this is the reference of the reference of the from where this formula has been derived, and it is used in this Excel application. Now, if you have got any problems, if you got any queries, my phone number and my email ID is given on each sheet. You may go to any sheet, and these details are given over here. You go to any sheet, and the address, email ID, and these things are given over. Here it is given. The phone number is given, and the email ID is given. So you can contact me if you have got any problems related to any of the calculations or any procedure in any of the sheets given over here. Thank you very much. And